Lecture 16, today is October 5th, 2016. You have a Friday off, fall break, so we have a long weekend to help you get ready for regular exam 1 next Monday. It is cumulative, our main topics being most of the stuff in chapters 7 and 8. Those stuff that came before chapters 5 and 6 should be reviewed. You should review the mini exam. The concepts in chapters 5 and 6 could certainly be on this exam as well, though they probably would be in the context of problems from chapters 7 and 8. You've already had the gateway, although some of you still need to pass it with retakes. Could there be plane integral problems on the regular exam? Yeah, there could be, though probably they'd be more focused on ones you were not tested on with the gateway. For example, trigonometric substitutions. The other kinds of things that come up, integration by parts, regular substitution, could come up on the test, but probably in the context of an application. An applied problem would be where they show up. I was hoping to get into some reasons why things work today, but in typing up a list of topics here before class in the Mathematica notebook, which I will make available for you on Moodle, I realize it's a long list and it's going to pretty much take us the whole time to go through it. I would like this to just be one lecture today with no break, and to help you through it, I will try to end class early. I'm shooting for 10 minutes early, finishing at 12:10, so hopefully, yeah, that would be 10 minutes early. Hopefully we can finish by then, so we'll go straight through without a break. Please stop me if you want to ask a question, okay? I'm sure if you have a question, other people have the same question. Other people may be watching the video in the future and have a similar kind of question. Please stop me. I want it to be interactive. If you have questions, for you to ask me questions about things, whether they are just things that you could be tested on, or if you don't understand something and I can clarify, let me know. So I've got this list. Again, I'll make this Mathematica notebook available for you that I typed up before class. In the bottom section of this notebook, things to know and be able to do on exam 1. I did, for sake of completeness, in the very first bullet point here, say you should certainly know the stuff from chapters 5 and 6, the fundamentals about integration, especially the Fundamental Theorem of Calculus in all of its forms. Maybe that's the first thing I should focus on. The form you are most used to is for evaluating definite integrals. Zoom in if you need to. Evaluating an integral like this, what do? Well, you have to find an antiderivative for little f. Hopefully you can find an antiderivative. Sometimes it's not possible, or sometimes it's just really hard. But once you've found the antiderivative, then doing capital F of b minus capital F of a, where capital F is your antiderivative, any antiderivative, that will calculate the definite integral for you. And of course, the area interpretation, the signed area interpretation. The graph is both above and below the axis. You take the area that's below the graph when it's above the axis, and subtract the area above the graph when it's below the axis. Right, you know that. If you're real familiar with that, you should be. Review that if you need to. So if capital F is an antiderivative of little f over an entire interval from a to b, that's how you calculate the integral. This equation can be turned around. It's sometimes useful to turn it around and think of this as a change in capital F, and emphasize that little f is the rate of change of big F. When you do that, sometimes people call it the total change theorem. It really is the Fundamental Theorem of Calculus in a different form. And the emphasis then is not so much on calculating the integral, but instead calculating the change in your function. To calculate the change in a function, integrate its rate of change, integrate its derivative. To calculate, for example, the displacement of an object, change in position, calculate the integral of its rate of change, its velocity. And sometimes You might not even have a formula for the velocity. Instead, you just have a graph. And you have to either estimate points on the graph and do left and right hand sums and average them, or if you've got a grid, count boxes, calculate the area of each box, add them up when the graph is above the axis, and subtract them when the graph is below the axis. Okay, I'm summarizing things you should be pretty familiar with right there. That helps you calculate the change in position in that context. Then there's the hardest part, what our book calls the second fundamental theorem of calculus. Not everybody calls it the second fundamental theorem of calculus. In fact, here's a little secret. Some people actually switch around the names. What you are used to calling the fundamental theorem of calculus here, they call the second fundamental theorem of calculus. So the naming is not consistent. They're all related to each other. It's probably better to call this the antiderivative construction theorem. It tells you how to differentiate an integral when your variable is in the upper limit of the integral. So x here is in the upper limit of the integral. It doesn't matter what your lower limit is. Any constant. Different constants will give you different antiderivatives of the integrand. Different a's will make this integral be a different function, a different antiderivative. But it is an antiderivative of little f. If you differentiate it, you get little f. And you should put an x there because the variable for this function is x. So it's kind of like the integral sign and the ddx kind of cancel. But you're differentiating with respect to x. Those three letters should be the same. This letter can be anything you want, except don't use an a, x, or f, or d. Those are already being used. So t, or tau, or whatever you want to use for that one. This is true even when you can't integrate f. You can't find a simple formula for the integral of f. This still mathematically constructs an antiderivative. Now, one kind of problem you're going to see in those practice problems I posted on Moodle yesterday is a problem like we did in one of the lectures, I don't know, maybe about 3 weeks ago or so. Today's lecture 16. It might have been lecture 5 or 6 or 7, where I drew a graph and I was thinking about the signed areas and verified by using formulas for areas of rectangles and triangles and trapezoids. There's a piecewise function and constructed an antiderivative. I was trying to illustrate the truth of that theorem in this context and also emphasize the area interpretation of the integral. You'll see a problem like that in the practice problems that I posted yesterday. There are a lot of problems, by the way, in that list of practice problems, more than would show up on your exam. There's no way that could be a 1 hour and 10-minute exam. By the way, I probably will give you extra time for the exam. Maybe we'll start 10 minutes early. So I'll probably try to give you an hour and 20 minutes for the exam. But there's no way you could do all those problems in an hour and 20 minutes. Okay? In fact, if you could finish them in 3 hours, that'd be pretty good. So I have to pick a sampling of those types of problems, or maybe something slightly different. There are other properties that I'm not talking about here. I'll mention a couple real quick. The integral of a sum is the sum of the integrals. That's called the linearity property. Okay, you know that, I think. That comes up in chapter 5. It's a very important property, actually, but we kind of use it without thinking about it much. Another example of a property in chapter 5 is that if you want to integrate a function from a to b, sometimes it's helpful to find some number c between a and b and do two separate integrals like this and add them together to get the final result. Typically, c is between a and b, though it actually doesn't have to be. It's typical. You go from a to c, then from c to b, you get the entire integral from a to b. Typically, c is between a and b. So those are a couple of properties in chapter 5 you should be able to know and use on the exam when you need to. All right, let's move on to chapter 7 and 8 stuff. So of course you should know the method of integration by substitution. There's your W substitution, or if you prefer U substitution, I don't care. Actually, I learned it as a U substitution in my old book. Our book, the reason they use W instead of U is they want to keep it distinct from integration by parts. So they use a different letter, they use a W. For finding antiderivatives, typical kinds of examples include these examples you see here. For this one, you're looking to let W be something, so that dW is almost there, like this x squared dx is almost dW. Yeah, if you let W equal x cubed plus 4, that'll do it, because then dW will be 3x squared dx, and x squared dx will be 1/3 dW, and you'll get the integral of 1/3 W to the 1/2 when you do that. So there's a typical kind of example. Another typical kind of example is with the products of powers of trig functions. You have this kind of thing on the gateway. If you haven't passed the gateway, you're going to want to pay extra close attention here. Where one of the powers is odd, if they're both even, it can get pretty nasty. You know, if there's a cosine to the 4th of x times sine to the 4th of x, it gets really nasty. It can be done, but it's a real big pain. So we make it a little easier, make it one of those powers odd. Whichever one is odd, or maybe they're both odd, then it wouldn't matter. Take that one with the odd power and peel off one of the powers. So if it's sine cubed, write it as sine squared times sine. If it were sine to the 5th, write it as sine to the 4th times sine. Sort of pair that thing up with the dx, and that gives you the hint that you should let W be cosine of x, because then dW will be negative sine of x dx. So that's what you do at that point, is you let W equal cos x, dW is negative sine x dx, and then you also need to use a trigonometric identity to help you finish it. Sine squared should get replaced by 1 minus cos squared. So then you'd have a W to the 4th right there, and also a 1 minus W squared right there. If this was sine to the 4th of x times sine of x, meaning it was sine to the 5th originally, do the same thing, but you'd have to square this thing, and so you'd have to expand it out. Although that would be easier to do with the W in there already. Okay, so these are kind of typical examples that you might encounter. Again, since these were gateway problems, most likely if these come up on the test, it'll be in the context of an application. You should be able to do these in applications. Either a differential equation, or a distance traveled, or a volume, or a probability. Those kinds of things. Trigonometric substitutions are always a bit tougher. Typically, the integrals involve square roots, though not always. Typically, they do. Sometimes they involve like something to the 3/2 power, which is still really involving a square root. If it happens to be of this form, commonly b is 1, by the way, when you look at that, but a is typically not 1. Use this substitution, and you can see why that's helpful. If you actually put it in there and square it, you're going to get a squared over b squared sine squared theta. And here you have an a squared over b squared. This minus that, because of the identity that 1 minus sine squared theta is cos squared theta, will equal a squared b over b squared cos squared theta. And then you take the square root and assume, for the sake of doing the integral, that you're in a values of theta are in the range where cosine theta is going to be positive, so you don't have to worry about absolute values when you take the square root. I'm saying all these comments here pretty fast, but I've mentioned them all before, and so I hope you've got a few neurons in your brain that can draw that connection here. Do you remember doing these things? dx is going to be that. Solving for theta will give you that. It will also be useful to use this identity not only here, but sometimes in other places after you take the square root. So that's, well, not always, but sometimes. That's typically helpful. It's helpful here. For integrals looking like this, involving square roots like that, with a plus sign there instead of a minus sign, and again, b is often 1, do tangent. Move this up here. So now we're focused on this thing here. You got a plus sign in there now. It's best to let x equal a over b tangent theta. Again, b is often 1. Not always, though. You should be able to handle it if it's not 1. Then dx is this, involving secant squared. Theta can be solved for with the arctangent. And this identity, that 1 plus tangent squared theta equals sine secant squared theta, that's often helpful. And again, you'll end up getting like the square root of secant squared theta, which is technically the absolute value of secant theta. But you assume you're in a range where that's positive for the sake of getting an answer, so you don't worry about the absolute value signs. You gotta practice these. I'm just summarizing what to do. You can't expect to get this without practicing it. Okay? We've got enough topics to do here that I'm not going to have time to practice really. You need to practice on your own. Practice on these integrals. Be able to justify this abstract formula right here. We did talk about that in class. I think it was maybe lecture 3 or 4. Am I looking for a proof here? Well, not really, because I'm not looking for complete sentences necessarily. Proof should be written in complete sentences. The only place I'd want you to do complete sentences is with the comparison test for improper integrals. I'm not looking for a proof so much here as just an understanding of why these are equal and maybe a little bit of explanation. I am assuming little f and little g exist. They're continuous and g is differentiable with a continuous derivative. Is sort of the background assumptions here so you can do these integrals. And I am assuming capital F, which is not written here, is assumed to be an antiderivative of little f. How is that relevant? Well, the way to verify that these are equal to each other, abstractly, is to use the fundamental theorem of calculus on both of them separately and see that you get the same thing. Based on this assumption, and you also end up needing the chain rule. The fact that capital F is an antiderivative of little f, well, and the FTC, of course, too, means that if you integrate little f, calling its variable w, but I could use a different letter, from one number to another, those numbers happen to be of the form g of a and g of b. Fundamental Theorem of Calculus says, calculate f of the top number minus f of the bottom number. The top number is g of b. The bottom number is g of a. So when you simplify the integral on the right side, assuming capital F is an antiderivative of little f, you get that. What about the left side? That's more complicated looking. Does this equal the same thing? The answer is yes. Why? Why does it equal the same thing? Partially it's the fundamental theorem of calculus and partially it's the chain rule. If you differentiate the function capital F of g of x, the chain rule says, and you should know this, take the derivative of the outside, plug in the inside, multiply times the derivative of the inside. That's the chain rule in abstract form. You should know that for the test. And, well, capital F, once again, is assumed to be an antiderivative of little f, so capital F prime is little f. They're the same thing by assumption. So what do we have here? We have the derivative of this function is the function we're integrating. Therefore, this function, capital F of g of x, is an antiderivative of this function we're integrating. So therefore, by the fundamental theorem of calculus, this integral also equals the exact same thing. Capital F of g minus capital F of g. I'm purposely leaving the inputs blank for the moment because I want to emphasize I plug in the upper limit b minus what I get when I plug in the lower limit a. I get the same answer. Up here, conceptually, we were imagining g of a and g of b being particular numbers that were being plugged into capital F. Here we're imagining a and b being particular numbers that are plugged into the function f of g of x, the composite function. There and there. What you get, they're the same symbol there, the same thing here. So the integrals must be the same too. So I wrote down those equations, I said things verbally that you should be able to briefly describe in writing.
Could you prove this as well with u substitution on the first or the left side of the equation?
Well, it's best to prove it this way. Essentially, this is justifying the substitution. This is substitution in abstract form. And essentially what we're doing here is we're saying that's okay.
Alright, is that, f prime g of x, where you have a square, because you have it written as f prime g of x on the board, but in the Mathematica, where you have the big box around it, so it just says f g of x, not f prime of g of x, but on the board you have f prime of g of x, so I was wondering which one it.
Oh, did I write it wrong? I wrote it wrong on the board.
Oh.
Thanks for catching that. This is no prime there. I'll have to make an annotation video. That was a mistake. Thanks for catching that. Okay. You should be able to relate this to a particular example as well. Like if we were integrating this one as a definite integral. We're doing this one from, I don't know, 1 to 3. For the sake of making the connection more clear, let me write it like this. 1/3 times the integral from 1 to 3 of 3x squared, square root of x cubed plus 4 dx. Focus on this integral here now and compare with these expressions. Focus on this one. That integral that I circled over there will be this one if g of x is the thing that you're letting w be really, which was x cubed plus 4, and f of x is the square root function, because that square root there, that's f of g of x, that matches this. And then g prime is 3x squared. G prime there matches the 3x squared right there. So you should be able to do the matching to understand how that integral is related to this one. And then when we do the substitution, again, let's just leave the 1/3 out in front, we really end up with f of w, which is w to the 1/2, square root of w. And if I change my limits of integration, this is going to be g of 1 and g of 3. G of 1 is what I get when I plug x equals 1 in here. That is going to be 5. And g of 3, I plug 3 into here. I get 27 plus 4 is 31. Sorry, this is kind of a mess here. Okay, so you should be able to see the connection with the abstract formula is the point. The 1/3 there just needs to be kept in front to keep the connection more clear. All right, let's go on. Integration by parts. Be able to use it, of course. What's a couple typical examples might be this kind, and this kind, and this kind. Here you'd want to let u equal x and v prime equal cos 2x. So So that u prime is 1 and v is going to be, in this example, 1/2 sine 2x. I'm essentially using a substitution in my head to figure out v. If you prefer using du and dv, which is okay, if you used integration by parts in a different form, you'd get a du is dx here, and you'd write dv is cos 2x dx. If you're used to that, you can do that. If you don't know what I'm talking about, you can ignore what I just said and just do it our book's way. When you've got natural log and or arctangent, hopefully not and actually, you actually want to let the u be the natural log in this case and u be the arctangent in this case. So that v prime is easy to integrate is the main reason there. V is going to be 1/4 x to the 4th in this example. In this example, v is going to be x. And u prime can be found 1 over x in this example, 1 over 1 plus x squared in this example. So it's a little bit opposite of the way we typically pick for u, but realize the more important thing here is that v prime can be integrated easily to find v. That's sort of the more important reason you pick these things the way you do in these kinds of examples. If the integral involves both natural log and arctangent of x, I think I had Mathematica try one of those and it was really nasty. Maybe it didn't involve non-elementary functions. Some part of the answer, it might not really be something you can write in terms of ordinary functions. Be able to justify this abstract formula. Actually, this is not one that I wrote down yet in class. By the way, right here, this could be written as u of x, v of x, evaluated from a to b. How do you justify that? It's the fundamental theorem of calculus again, as well as the product rule instead of the chain rule, and then some properties of integrals after that point. Essentially, here's the way you want to think of it. If you want to imagine integrating something, if you think about integrating something like this, u of x, v prime of x, plus u prime of x, v of x. You look at an expression like that, that should seem real familiar from Calc 1. The first times the derivative of the second plus the derivative of the first times the second. That should look like the derivative of a product, and it does. It does look like the derivative of u of x times v of x by the product rule. That's true by the product rule. You're assuming your functions are nicely differentiable. And it also works to make sure you're nicely if your derivatives are continuous. Everything's nice here. So you're integrating a derivative of something by the fundamental theorem of calculus. This is the product rule right there. By the fundamental theorem of calculus, find an antiderivative of this and plug in b and subtract what you get and plug in a. But hey, that's easy. U of x times v of x is an antiderivative of this derivative by definition, because it's the derivative of that. It's so easy, it's confusing. Catch that? I'll say it again. What's an antiderivative of this derivative? This is a derivative of that. Therefore, an antiderivative of that is this. An antiderivative of the whole thing is the inner thing. Plug in b, subtract what you get when you plug in a. U of b, v of b, minus u of a, v of a. Then we're actually, that's the FTC, then we're almost finished actually. Because we can, to get it to look like this, all we need to do is use the fact that this integral is equal to the sum of two integrals. And then solve for this integral of u times v prime, by subtracting that integral from both sides. And that's the integral that shows up on the other side, except I switched the u prime and the v around. That may have gone by too fast. If you're feeling a little sleepy, to get it, take the time after class to think about it. It's actually, I think it's easier than the substitution one to think about. That's because of the product rule, that's because of the FTC, and then just use effective physicals that and do a little algebra to write this equation. When you do substitution, when you do integration by parts with definite integrals, you don't have to change the limits of integration. Don't do it. When you do substitutions, you do. The A and the B stay the same. Partial fractions. Should be able to use the method for finding antiderivatives. Typical examples include things like this and this. We did do the simplest cases where you could factor the bottom and also, well, you didn't have any factors that were repeated factors. That makes it a little tougher. We will focus on the exam on the simplest cases. In both of these examples, you want to try to write the integrand as a over x plus 3 plus b over 4 minus x, and solve for a and b. In both of these cases, same kind of decomposition. The numerator is different, 1 and x, but so you're going to get different a's and b's, but in both kinds of examples they should work. This kind of decomposition should work. And then integrating these is easy. When you integrate something like this, you get a times the natural log of the absolute value of x plus 3. And careful, because of that minus sign there, I purposely put a minus sign in there, you're going to get a minus sign here. Two quick ways you can justify that in your mind. Oops, forgot my b. Two quick ways you can justify that in your mind. You could imagine differentiating this and realizing because of the chain rule, oops, sorry. Well, actually you can write it like this. But, more typically we're going to write it like this. Because of the chain rule, you get an extra factor of -1. Which does bring up a question. How does that justification happen in the context where it is x minus 4 in absolute value? I'm not going to worry about that. We typically write it like that. Another way you can justify it is imagine doing a w substitution here. W is 4 minus x. dw would be negative dx. The negative sign there is another way you can informally justify it. I got to think about that case where you switch these around, because technically it's still the same function if you switch those around as the absolute value signs. I don't want to take the time for that though. Will long division show up? It could. I'm not ruling it out. You have to use long division before you do partial fractions if the numerator has the same or higher degree than the denominator. So in this example and this example, you got an x squared and an x cubed on top. Degree equal to or greater than the degree of the bottom, which is 2. In those cases, you got to use long division first before you try using partial fractions. For example, in this case, x cubed is being divided by negative x squared plus x plus 12. To do that long division, what do you multiply negative x squared by to get x cubed? You multiply it by negative x. Do the multiplication now. Then subtract. Since you're subtracting negatives, they're going to become positives. You got to multiply negative x squared by -1 to get x squared. Once again, multiply and subtract. Careful, subtracting. That's going to be the remainder. Did I make a mistake?
Well, yeah, why would it be 13x? I think it would be better if you put a subtraction sign by the x squared minus x plus 12.
Sorry, running as x squared minus x minus 12, you could do that. You'd have to put a minus sign in front of this then.
I just meant when
You can do it
doing
this
your
way, though.
equation, I just don't see a minus sign by the, when you're long dividing.
Mm-hmm.
I don't see a minus sign there, and that can be confusing.
Where?
Down where you take x squared plus 12x.
Oh, so you're saying go ahead and put a minus sign in there like that?
I think that would just be.
Yeah, that's helpful for you. Go ahead and do that. That would be the remainder, and what this would mean is that this function right here is equal to the quotient, which is negative x minus 1, plus the remainder, 13x, so plus 12, divided by the original thing you were dividing by here, like that. And that's easier to integrate. You'd integrate this very easily, and this one you'd have to use partial fractions for, based on the factored form. You'd have to do this kind of thing again with this part, but it's doable. It's complicated enough that maybe I'd give you help or something if I put a problem like this on the test. Tables, be able to use a table when it's given to you, okay? What might be the most likely kind of problem where I give you a table equation and ask you to use it? Perhaps integrating products of sines and cosines of different frequencies might be the most likely kind of example I give you in the table. It's a pretty useful kind of integral with something called Fourier series, which we'll talk about a little bit at the end of chapter 10, I believe. But it's not typically an integral that we teach without either using trigonometric identities or using a table. One or the other is the best way to go with those, and either way you do it, you're pretty much using something that you're looking up or memorizing. But I'd give you a table equation from the table, and you just need to use it. Trigonometric identities, these are the two most fundamental to use that I haven't talked about yet, that allow you to integrate, for example, cos squared theta and sine squared theta pretty easily. You can also integrate cos squared theta or sine squared theta by doing it by parts, but it's easier using those identities. By the way, you can use a note card on the exam, front and back, to write formulas on, so maybe you want to write these formulas on them. The note card is supposed to be there mostly just as an anxiety reducer. You should study well enough that you think you could do well without a note card. It's mostly there as your security note card, security blanket kind of thing, anxiety reducer. I would suggest trying to resist using it during the test, because otherwise, if you're relying on it too much, people just spend too much time looking for their note card, sometimes in vain for something, and it wastes a lot of time. So study well enough, practice problems enough that you think you could do well without a note card, and then you keep it there just as your security. Helps to reduce the anxiety. Oh well, time's going by fast for me. It might be slow for you. Only 20 minutes left to try to aim to be done. Other topics, and there's plenty of other topics. Numerical methods. There's the basic setup. You're given a nice continuous function over a closed interval and a positive integer n, the number of subintervals. You first define delta x or delta t, depending on the application. It would be b minus a over n. That'll be the width of each little subinterval. You let xi be a plus I times delta x, and in typical examples, we typically let a be 0, but it doesn't have to be. This equation should make sense to you. For example, it says that x1 is a plus delta x. It says that x2 is a plus 2 times delta x, etc. So to get from x0 to x1, you have to add delta x. To get to x2, you add another delta x, etc. This equation does make good sense that way. And then you define your left-hand sums, right-hand sums, trapezoid, midpoint, Simpson's rules, with these equations involving summations with the left and right and with the mid. And then our book's approach is to use a sort of experimental approach based on the errors with these things to define trapezoid in Simpson's rule. You may never have seen these equations before if you've taken Calc 2. Maybe you did the trapezoid rule and Simpson's rule with a different method. I want you to use our books. I want you to do it this way. Okay, so that does involve calculating other things first. If you do Simpson's rule, you actually have to calculate all of them, which I think is good to be able to do. If I have you want to do one on the test by hand with calculator help, probably I'll let n equal 2 to keep the calculations to a minimum. Actually, you can even do n equals 1 and see what happens. For any method, the error is the actual value minus the approximate value. And I remember the order of those things because actual comes before approximate in alphabetical order in the dictionary. Although people don't look things up in dictionaries anymore. You know, AC comes before AP, and that's how I remember the order of it. You could also do it as actual value minus estimated value, and A comes before E as well. For increasing functions, whose graphs are going up, whether they are concave down, concave up, or both, the left-hand sum will be an underestimate. You'll get rectangles that look like this for left-hand sums. And the right-hand sum will be an overestimate. Underestimates actually have positive errors. That's a little confusing. The reason is because of the order of this. If the approximate is too small, this number is bigger than that, so the difference is going to be positive. Overestimates have negative errors. If the approximation is too big, this number minus that number will be negative. So it's a little funny that way, but it's something you should be able to deal with. For concave up, functions coming down here to mid and trap. Mid is an underestimate and trap is an overestimate. If you've got a concave up function, a trapezoid rule with one trapezoid looks like that, and you get an estimate too big. I didn't explain why, but you can think of the midpoint rule in terms of trapezoids as well, though instead of having the top of the trapezoid be the secant line between 2 points, you have it be the tangent line of the midpoint, so you end up getting another trapezoid whose area is too small when the graph is concave up. I didn't explain that you can think of the midpoint rule in terms of trapezoids as well. The book does explain it a little bit, essentially by rotating, well, okay, I guess I could kind of explain it right now. By rotating this tangent line about this point, you get a rectangle there that is the rectangle from the midpoint rule, and because it's a rigid rotation about that point, the area of that rectangle is the same as the area of the trapezoid. The height of this rectangle is the same as the average of the heights of the trapezoid, with the red top here and here. If it's concave down function, looking at the bottom here, mid is an overestimate and trap is an underestimate. And you could draw the concave down function to see that. More factual information to know. Actually, some of the things I wrote on here is a little bit new. For the left and the right hand rules, the error actually is approximately k over n for some constant k, at least when n is sufficiently large. That's something new. I didn't write that down before. What that means is something that I did write down before. One extra digit of accuracy is obtained by doing 10 times the work. If you increase n by a factor of 10, like from 2 to 20 or from 3 to 30, you get one more decimal place of accuracy. The error essentially gets divided by 10, approximately. For trap and mid, the error is actually proportional approximately to 1 over n squared. And since 10 squared is 100, that means if you get 2 extra digits of accuracy by doing 10 times the work. If you increase n by a factor of 10, like from 2 to 20, that fraction goes down by a factor of 100. 1 over 2 squared is 1/4. 1 over 20 squared is 1/400. 100 times smaller. Mid and trap also tend to have opposite signs for large enough n, and that's why we define Simpson's rule as a weighted average, and the midpoint rule is about twice as good. Midpoint rules, the error in the midpoint rule is about half as much in absolute value as the error in the trapezoid rule, meaning the midpoint rule is about twice as good. And they tend to have opposite signs, which is why we give, in Simpson's rule, the formula we use, we give the midpoint rule twice the weight of the trapezoid rule because it's twice as good. Turns out the error is approximately a constant over 10 to the fourth. Since 10 to the fourth is 10,000, you get 4 extra digits of accuracy by doing 10 times the work. Okay, those statements are in the books. Those approximations for the error are not in the book, but you'll see them in other books.
I just had a question over the way you drew the midpoint rule.
Mm-hmm.
Is the correct way with the tangent line, or is the correct way with the...
With the tangent line.
That's the correct way.
The secant line to make the trapezoid is for the trapezoid rule.
No, but like, you also drew it horizontal.
Yeah.
To the
The
x-axis.
definition of the midpoint rule is based on rectangles, not trapezoids. And so I went up, I used the midpoint of the interval to go up to the graph, and then if you rotate that horizontal line to become a tangent line at that point, you get a trapezoid that has the same area as the original rectangle. I know I'm going fast. You can rewatch the video too if you feel like you need to hear me say something again. It's another benefit to you guys in the video. More topics, improper integrals. There's a lot of topics that could be on this test. They're all connected to each other in some way or another. They're all connected to integrals. Be able to calculate improper integrals, for example, in terms of a limit like this. Although to finish this calculation, you'd also have to do the integration by parts. U equals x, b prime equals e to the negative x. That's improper in the upper limit. There's an infinity here. This kind of integral is improper in the lower limit because you've got a vertical asymptote for this function, 0. So it's a limit as the lower limit goes to 0 from the right for the square root function of something like that. So you should be able to do these calculations. You may use the fact that I told you the other day, if, maybe I mentioned this somewhere else. I guess I mentioned it here, kind of. It's not exactly the same statement. As long as A is positive, so that negative A is negative, N can be anything. You may use this as a fact, the fact that this is 0 no matter what. This should be a B here, sorry. If A is negative there, the exponential decay sort of overwhelms the power function to such a degree that the product goes to 0 eventually as B goes to infinity. The graph may go up real high initially, but it's eventually going to come down because of that exponential decay in there. You can use that as a fact that you might need. There's some facts to know. This integral converges when p is bigger than 1 and diverges when p is less than or equal to 1. This integral, where the impropriety is at the 0, converges when p is less than 1 and diverges when p is greater than or equal to 1. So it switches. Though they both diverge when p equals 1. And the reason ultimately is because the natural log function both goes to infinity as x goes to infinity and goes down to minus infinity as x goes to 0. That's why they both end up diverging when p is equal to 1. So you'll get a natural log when you do the integral. You can also know that this kind of integral converges as long as a is greater than 0 and n can be any n greater than or equal to 0 there as well. Those are useful integrals for comparison test proofs. If I have you do a comparison test proof on the test, you should write sentences. I will probably give you a little guidance as to what to pick for f of x and what to pick for g of x, and then you just need to verify the hypotheses of the comparison test. There's statements in the book, for example, that the function you're integrating is between 0 and g of x for all x, and knowing that the integral of g of x converges, the comparison test then allows you to say the integral for f of x converges. You must put the integral signs in there, though. That's something I really emphasized in the example that I did about a week ago. We did an example like that. Okay, that's the biggest problem people seem to have when I've graded those kinds of proofs in the past, that they forget to put the integral sign in them. It's the integral that you're interested in proving the convergence of. Applications. 4 main classes of applications, and I've got lots of details. I think I'm going to summarize this stuff really quick because we're running a long time. One type of application was to differential equations. That we didn't spend a ton of time with differential equations, but a little bit. Here's your differential equation. Here's your initial value. Combine those two things in one problem. You call it an initial value problem. Differential equations have general solutions. Essentially, in the first case, you have pure antiderivatives that represent infinitely many possible answers. But when you add an initial condition, you get one unique answer. And if the right-hand side is just dependent on x here, this is the same as an antiderivative. You just want to find the indefinite integral of x cubed plus sine 2x. And then choose the c in such a way that y of 0 is 4. In this case, you get 1/4 x to the 4th minus 1/2 cos 2x plus c. I did a substitution in my head there. That's y. In order to make y of 0 equal to 4, I need to choose the c so that this is true. Cosine of 0 is 1. So this is a negative 1/2 here, and I have to add a 1/2 to both sides. It looks like c has to be 4.5 to make this work. 9/2. I've not made a mistake. This kind of differential equation is a bit tougher. Now the right-hand side depends on the function, the y, so to speak. To find y as a function of x here, you have to separate variables first. And this is the most common basic type like this. You want to write it like this. And then you feel this urge to integrate both sides. You separated variables, you get the y's on one side and the x's on the other. The x's is just a dx. This is easy to integrate. You get x plus c, or maybe you want to call it c1. That's harder to integrate. You've got to use partial fractions and get logarithms. You ultimately have to exponentiate to solve for y as a function of x and use the initial condition to find the constant that you get. It's more complicated. I'm not taking the time to finish it. I'm going to say you will have a problem similar to this on the exam, which means you should practice it. You should go back and watch the lecture where I did it. I think it was only in one part of one lecture where I did this kind of problem. It's a fairly, even after doing the integral, the algebra is fairly tricky. So definitely you're going to want to practice one like this. It's useful for modeling population growth. It's called the logistic model. The graph of the solution looks like this. It goes concave up and then becomes concave down and has a limiting value. Talked about that with populations. So I think only in 1/2 of a lecture A or lecture B from one lecture a couple weeks ago maybe. So practice that. There are examples in the book as well. Understand the idea of a system of parametric equations leading to a parametric curve. Be able to graph it with your calculator. You should make sure you can do that. Make sure you know how to use parametric mode in your calculator if you haven't yet. And I should add Mathematica code here as well. You should be able to use parametric plot. Parametric. I'm sure you spelled it right. parametric plot with a capital P in the first spot and a capital P in the second spot, as well as manipulate with capital M to write down code by hand that would give you an animation for a graph like this. Commas, square brackets, curly braces need to be put in appropriate spots. That I will give you one kind of Mathematica problem like that. You're writing down basic Mathematica code. Just to get a graph, that would be an animation. You don't have to worry about, I'm going to say, don't worry about plot range or plot style, thick and red, all that kind of stuff. Get the basic stuff involving parametric plot and manipulate right. Given a function that you inputted already, C of t, say. Input it like this. I'm going to say don't worry about this. Pretend you've already done this. You've already defined C of t based on f of t and g of t. Pretend that you've done that. Then just combine those two in an appropriate way. And I do have to be picky in grading it. It's got to be syntax that would work to make an animation of the curve that would show the motion as t varies over some interval. You're able to calculate the speed and distance traveled. There's the formula for the speed. Here's the formula for the distance traveled. Integrate the speed from 0 to t. Or, we can do that as a definite integral, or you can do it as an indefinite integral and just choose the constant c to make sure that that antiderivative goes to the origin. You want the distance at time 0 to be 0. You want your antiderivative to go, a graph that goes to the origin. This is sort of the main stuff I emphasized in my videos that you hopefully watched a good chunk of. The distance is the antiderivative, an antiderivative of the speed. The speed is the derivative of the distance traveled. What about vectors? Oh, we're not going to quite finish by 12:10 here. I was aiming for it, but it's just not possible, I guess. What about vectors? I wrote the vector notation up here with the I hat and the J hat just for sake of completion, but I think really the only thing I can test you on with vectors is like if you sketch the parametric curve, you should be able to like sketch the position vector and sketch the velocity vector in the picture. That's the main thing we focused on. Make sure the position vector is based at the origin, is pointing at whatever time, maybe time 2 or time 3, at the location of the object at that time. And make sure your velocity vector is drawn to be tangent to the curve at that point, pointing in the direction of motion. The length of the velocity vector you should know is the same as the speed, and maybe I'd ask you to state that or know it in a multiple choice question or something. The length of the velocity vector as an arrow is equal to the speed. This notation, I think I'm not going to test you on, but I have it there just for the sake of completion. Polar coordinates, you should be able to convert back and forth between polar and rectangular with these equations. More importantly, there's the idea of a polar graph and how to graph it, and using your calculator in polar mode. So practice that a bit if you've never done that. You know, f of theta equals theta, or f of theta equals theta squared of the two main examples we looked at. You get the spiral behavior when you're using polar coordinates there. You can view a polar graph in terms of parametric equations. Theta now is the parameter instead of t, though you can pretend it's time if you want. You can pretend the angle is the same as time, just for the sake of conceptual clarity. The speed, the formula is given in the book this way. However, we saw in the last lecture that simplifies to this when r equals f of theta is your polar equation, because the cosquared theta and the plus sine squared theta terms that come in from differentiating these with the product rule end up equaling 1, and you end up simplifying. So you can integrate just that to find the distance traveled, same as the arc length. Though again, these integrals typically end up being difficult. Maybe I'd combine an integral like this with a numerical method problem. Since the integrals are so difficult to do, sometimes you have to use numerical methods.